All right, welcome back. So one of the fundamental aspects of programming that was added in C#5 was the async await. And these kind of help you deal a lot more easily with parallel programming or executing things in different threads. So both C# and JavaScript have these keywords async and await. And if you use both of them together, the compiler will automatically help you and break your execution of your code into smaller chunks. Okay. Um, does this mean threads? Well, threads is a different concept. This will actually break your code down, and we're going to talk about threads and how this all works kind of here as we go through this. So one of the reasons to really look at this from the game development standpoint is this is used in Unity all over the place now with loading prefabs, particularly with addressables. Um, and we'll kind of maybe look at a walkthrough on that. So before we get into details, why and when do you need these? So a lot of times when you're working with something that has a user interface, if you're doing a lot of computation or if you're waiting to load something, your mouse won't respond. So all the buttons will look like they're valid, but if you try clicking on it, the main thread is they're busy working on your code, working on trying to load something. And so your application seems unresponsive. Seems like it crashed or hanged, what have you. And so that's a bad thing. We want to avoid that. So this is kind of one of the best use cases, or one of the primary use cases, is to just allow work to be spawned off to free up the main thread to handle any kind of user events. Okay. File I/O a lot of times is asynchronous now, so and you can either keep checking if it's complete, or you can register a callback to notify you when it's complete. So again, if you do this on the UI thread, the application becomes unresponsive. So the developers of the language decided let's add some compiler help to help us all do this, so we don't have to really be experts in threading and whatnot. Okay, so when we talk about threads, really you should think in terms of three things, right? So what we'll primarily focus on is the application software, some abstraction of threads. Execute some tasks separately than some chunk of code B. And this may or may not have any kind of mapping to operating system threads. Okay, these are the ones that kind of say, oh, okay, I'm only going to let you run for a little bit, and then I'm going to run some other process. I mean, if you open up the task manager on even your private machine, you have thousands of applications running. And if you want any of those to be responsive, the operating system basically is going to say, hey, you get a little bit of time, I get a little bit of time, and everything will go through nicely, okay? But it also kind of determines that, okay, you're ready to run, I'm going to put you on the hardware, okay? And then there's also the concept of hardware threads, and this is basically at the lowest level. If there's a stall in the memory, the register needs to be loaded, then it can switch over to another thread, kind of the hyper-threading that Intel put in many years ago. Things like the Xbox 360, they didn't even have an operating system, so you actually had to manage this yourself. You were allowed 2 threads per core, and so you had to schedule which thread was going to run on each core. But think of this as basically if there's a memory delay, a different program counter will come in and continue execution on some other chunk of code. But the main one we'll focus on is this application software abstraction. Okay, so think of tasks as being jobs to be performed. I might want to read from a database, then I want to sort things, then I want to update addresses, okay? So again, the tasks have nothing to do with threads. Let me repeat that. Nothing to do with threads. How the threads are going to work on the operating system and the hardware is totally different. Think of threads as your workers. You could have a single worker performing all the tasks, or you could have different threads at different times work on a single task. Now, the whole point of this is we want at least a couple threads working on our task so we can have some sort of response, right? Responsiveness. All right, so there's 2 really modes of breaking your program down into tasks. One is called a task decomposition. So you're going to break your program down into subtasks that, and the kind of the flow, the data flow diagram for that. The other one which you hear a lot about is the SIMD kind of thing, parallel processing, where you do a domain decomposition. You're breaking your simulation into smaller data chunks. So a big for loop can run in parallel, single instruction, multiple data type path. Okay. For .NET, in particular, we're going to focus mainly on task decomposition. But for .NET, they have this class task. It's a generic class. It'll take a template. And it provides a wrapper for scheduling work, within some delegate function. So you pass it some function of type T, and it will wrap this around it. And you have some operations you can do, like run, which will schedule it, okay, or wait for the task. Now, task.run actually is a static method. So if I pass that function into it, it will create a task and schedule it, okay? And then these will run on the thread pool. So you don't have to manage threads, pools, or anything like that. The .NET framework will take care of that for you, okay? It's important to note that you can create a task. So if I say my task, new task, and I give it this lambda function here, it creates a task, but it doesn't execute it, okay? And there's a few ways to get it started. We're going to focus on the await keyword. But you can call mytask.start if you want to do your own explicit task handling. That is certainly valid. Okay, so I'll encourage you to take a look at the task documentation. You have some asynchronous state, some synchronous results. We always used to use begin invoke, end invoke for GUI controls, so those were quite popular. But we're going to focus on the async await and some easy use cases. Okay, so let's say we have this simple program. And so, I've done some good, functional style programming, structured programming. My work had, maybe 100 lines of code, and I broke it down into 3 methods that are going to hopefully be very cohesive, as you'll hear in different classes. Job 1, job 2, job 3. So, not the most elegant example here. So I want to decide which of these jobs can be done independent, okay? If, job 2 depends upon job 1 and job 3 depends upon job 2, then I really can't do much kind of parallel processing. But if my work doesn't depend, who's calling my work doesn't depend on the results right away, then we can kind of pepper that as well, okay? So in this example, let's say that job 3 is independent, but job 2 requires job 1 to be finished before it starts. All right, so all we have to do to get this to work is we're going to decorate our method. We're going to put, rather than these void return types, we're going to put an async task. And if I was returning a value, I would have a generic task value there, okay? And then I'll propagate this up even farther. I'm going to replace the void return type for my work with an async task as well. And then so anybody calling my work can perform that, as they can wait for it right away, or they can let it run in the background while they do other stuff. Okay, and then the third thing we're going to do is call await before all the calls to job 1, job 2, job 3. So very simple, looks like this. So now we have void async task my work. We're going to wait for job 1, we're going to wait for job 2, and we're going to wait for job 3. And likewise, I've done an async task job 1, job 2, job 3. And within these, I'm going to also need an await for them to work. So, or at least return a task. So let's, real quick, if we run this, you'll see what's happening. Whoever calls my work has some flexibility there, but all 3 jobs are still executed sequential. So it's the await in the previous slide here is going to require, is going to require the job 1 to finish before job 2 finishes before job 3. Okay. So behind the scene, though, the compiler is working to create several delegates, and some state machine. So it's writing a whole bunch of new classes, new code to execute this properly. So in this example, there would be 4 states. It'd be working on job 1, and now I'm working on job 2. Now I'm working on job 3, and now I'm finished with my work. Okay. One way to look at this is very similar to kind of a yield return. Control will return to the calling method, and then we'll resume to call job 2 at a later time frame. So I'm going to return back to the calling method. It can do some more work. It can do whatever. And at some point in time, it'll come back in and call job 2. Unlike kind of that explicit, you had control over those yield returns with your for loop or whatever you were doing inside your for loop of those. The framework kind of handles all this calling and execution for you. Okay, so each time it comes back into my work it'll restore the state needed for what it needs to be do next. So if it's job 2, it's the state to continue with job 2. If it's job 3, it's the state it needs to continue for job 3. Okay, so the only thing we've really done now is the calling method is free to continue to work on other things. So it can handle mouse clicks, etc. Job 1 is typically going to be executed from a thread pool. So we do have multi-threading, but our jobs within my task are sequential. So let's look at fixing that real quick. So job 2 we decided is dependent upon job 1. So I can't start it until after job 1. But job 3 I can jump in front of job 2. So I'm going to restructure my work to have a task that comes from job 1. I'm going to have a task that comes from job 3. I put var here, but this really is going to be a type of task. So I probably should have done that more explicitly. And then I'm going to tell it that, hey, we need to wait for task 1 to finish. Okay. Now, since I wanted to make my work async, as soon as I hit this await, it's going to return. So my work will return to the calling thread. The calling thread can keep working. When task 1 is finished, it'll come back into my work, and then it will say, oh, hey, let's do some work on job 2. At which point in time, okay, it's going to return again from my work, and then it will come back in. Okay, so now job 1 and job 2 are going to run while job 3 can execute. So we started a new task with job 1, we started a new task with job 3, and the await basically will tell that task to go ahead and fire, or sorry, whatever's in job 1 and job 3, it needs to tell what's going on to make sure it's started and running. Okay. And then we'll return control of the caller. Once job 1's complete, we'll come back. Once job 2 is complete, we'll come back. There are some efficiencies in this such that, if job 3 is already done by the time I call await job 3, then it boils down to be basically a no op, and it'll just finish up with my work there. Okay, so here's kind of an example you can look at here. So black here is the main thread. So if we call main, we jump into call count. Okay, so call count will be executed. It's going to keep going. Call count is an async task. Call count in this example creates a new task. And again, this doesn't really start a task or anything. This just has a new task, which is going to call this function count, which is down here. Okay, so we've started a task, and now we call task.start. Okay, and so that will hit a different thread, and so count will start executing on this new orange thread. Okay, and I'm just gonna, since I haven't said, hey, let's stop and return to the caller yet, I'm going to just keep executing whatever I want here. So I could have a very lengthy computation here, in which case, again, I'm stalling that main thread, and maybe I don't want to do it. It's not until I get down to this await that the state machine will jump back up to main. Okay, and says, okay, let's keep going through main. And again, if I had a bunch of work to do here, respond to whatever, I could do that. Okay. And at some point in time here, I'll say task.wait, in which case it's going to say, okay, now I'm going to stall until this task is finished. In the meantime, this task has been busy going on. And you'll see it's this orange thread, and at some point in time it will return to here. And now my weighted task is going to be able to join back in here, come back, and keep going. So your main thread is now this blue thread and not necessarily the black thread. So it'll switch threads on you there, which is fine. So that's kind of the execution order. The await and the async work together. If you try to create an async method without an await, you'll get a compiler warning or error. If you try to create a wait without an async, you'll get a warning. Async without a wait, you'll get an error. Okay. And there's some nice helpers in here. So if I spawn off a whole bunch of tasks to work, I kind of just want to say, hey, everybody go off and do their work. And when you're done, I kind of need to get you back together and do a little extra work. So there's two really nice, helpful utilities there. One is when any. So anytime a task is done, you can proceed to kind of do that. So if I'm opening a whole bunch of files and reading a whole bunch of files, and I don't care what order they come in, then as soon as one's done, I'll be able to work on it, and then I can kind of remove it from my list and call when any again. The other one that's probably even more popular is when all. So I want, when the whole thing is done, let me know, and I'll resume working on things. Okay, and so there's several tutorials out there you can look at, as well as some documentation from Microsoft as well. Okay, so again, just a few little gotchas. Task assumes, task.wait assumes the task is running. So if I did task.run to create the task, it's fine. But if I do the following, it will hang. If I say task one, await job one, actually this is a bad example, and then I say task one.wait, the reason this will hang is because this was already a task that completed. Once I say await, so now what am I waiting on? The task basically is over, and you're telling it to go ahead and wait until it's over again. So it's almost like it needs to rerun. So this type of thing short circuits that state machine. So if you're going to use a wait, kind of be careful with calling wait in that same block. Okay. If you, excuse me, if for some reason you really don't want to, you don't have a need for async, it's very simple. So here's an example. I created an interface for a spawner, basically, that has a method in the interface that says create. So this is basically, it wants to create a prefab or create a game object. So the return type is game object. And, it takes some information. In this case, really the position is the only thing that matters. This is just kind of extra data to help things. So the simplest one here is I'm just going to spawn an empty game object. So that's one of my classes that support this interface. Okay. And so the internals of that are basically very simple. It's new game object, which immediately returns, maybe set the local position, and then it will return a new game object. There's nothing that's going to, take any amount of time. So there's no reason for any sort of, spawn a thread off or anything like that. Okay. So there's three ways to do this. One is this first chunk here, new game object, blah, 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 return new game object. So this will always happen. And then there's actually three ways to return it. If I return a new game object, I'll get a compiler warning that it doesn't wait. You know, which is okay, even though I was told it was async or, yeah. The, that might actually give an error there. I'll have to go back and check that. The other way is, there's two other ways here. There's an await, and again, these are helper things. There's a task.completed task. So this is basically an instance of a task that will just always say, hey, I'm done, I'm done. And so once it's done, I'll return the new game object, okay? So this will be kind of, this should boil down to a no-op, okay? Another nice utility in the task class is, you know, just wrap a completed task from the result that I'm going to give you here. So these are both very synchronous options, and these would be preferred over, you know, getting the compiler warning or possible error here. Since I don't return a task, I return a game object. But just so you have that information, that's kind of a nice way to work around it. Because when you start putting the async into interfaces, you know, everybody who wants to implement that interface has to support it. And that's where these problems can arise. I guess here's the full. So this is a prefab selector async. So this is basically going to create it. So this was my interface for a spawner. And then here is a implementation that's going to just create an empty game object. Okay. So again, this will return synchronously. There's no work or for a task to do. It'll basically, anytime it's called, should just return immediately. With C#.8 and .NET Core 3, they added the ability to do this with enumerables, which means it had to propagate down into enumerators. And so now you have, rather than move next in your implementation of enumerator, you have move next async, and tcurrent will still stay the same. And then since you also have to add a async disposable rather than a disposable for this, and there's some other documentation and tutorials on that you can look at. With those enumerators, though, it also has to change the for each. So rather than do a for each, I'm going to do an await for each. Okay, and so I'll just stall the for each every time until its element is done. Okay. And then once that's completed, I can access the current property. So that just that's a nice way to have the for each. It's not a parallel for, it's, I'm going to await for every move next. And you can write classes that support the async enumerable or any kind of method that returns an async enumerable exactly as before. The difference is you're going to use awaits within your method, and the for loop will have, or the for each will have a await in front of it. So here's a simple example of that. So here I have a print int that's going to return an I async enumerable of int. In this case, I just put a simple little delay, sleep, I guess, right? So it'll return I, but it'll return I every second. Okay, so it's going to wait a second, return I, wait a second, return I, wait a second, return I. So again, if I want to spawn something every second, this might be a good example of that. So, okay, so that's kind of a quick overview of async await, and you're going to see it more and more and more in examples and usage of libraries. It does kind of require this propagation of async await up your chain of calling methods, but is a very powerful and useful feature. Thank you. Okay, and I guess the last comment I'll make there is, again, the compiler you don't actually execute this code. The compiler is going to take this yield return and create a whole bunch of new classes, much like it did with IEnumerable.